Okay, you watch it? Here's the test. All right, first side, front side, 4 problems. What are those 4 problems going to be? Well, I'm actually going to break down this guy into 2 problems. One's going to say, calculate the mass deficiency or mass defect, and the second problem is going to say, using that, calculate the nuclear binding energy. Next 2 problems are half-life problems. They'll be kind of like 2 or 3. All right, 4 I just put on there because there was one in the homework like that, or a couple in the homework like that, but they're not really half-life problems. They're just conversion problems. All right. That's the front side. Back side, plenty of equations, okay, on the first half of the back side, like these. And I'll ask you to both complete them, name the type of radiation, and whether you would expect that from a guy above or below the band. We'll do all of those in a little bit. Bottom part of this back side, the second half of the back side. That's going to be the hardest part probably, because it's going to actually ask you to study some stuff. Let's talk about that now in case I run out of time in the review. You're going to have some questions on the different ways to measure radiation, Curie's, RADs, REMs, and what they mean. So you better read that over. My guess is you don't remember that. You're going to have some questions, quite a few, on the types of reactors. That packet I gave you on the reactor types would be all the information you would need, but you're going to have to study it. What kind of moderator is used in our power plant versus what was used in Chernobyl. Now, from all the research you did and from all the talk we did about the accidents, you should know some of these answers just from that. But you should study it anyway because you have to talk about what kind of fuel it is and make sure you know which ones are which. Also, there are certain ones like the breeder reactors we didn't talk a whole lot about, but they're in there. Then we're going to talk a little bit about radiation and sources and health effects. So let's think about that. What are some sources of radiation? Just every day you're exposed to radiation from what? The sun, the earth, yeah, pretty much. And if you're flying in an airplane, you're closer to the sun. You're less air in the way to block it. You're going to get more radiation. If you're in the Rockies, which are naturally, rocks are radioactive, you're going to get more background radiation. I would ask you what kind of cells in your body are more susceptible to radiation. I'm going to ask you what kind of radiation is more penetrating, so it's more you have to worry about more, has more energy to it or whatever. So all those kind of questions I'm going to ask you in that bottom like 2 or 3 multiple choice sections or whatever. So the bottom, this is not going to be the essays are also tomorrow too, and I think I mentioned that yesterday because I didn't think I'd have a whole lot of time. Remember yesterday I told you here's your essay test. They just took it in their class. I'm sure they'll tell you about it too. One of the essay questions will be describe one of those accidents that you researched very well, okay, with all the detail. I don't care which one you pick. The second question will be actually 2 questions. We get to pick 2 out of 3 from the articles and video clips I showed you over the course of the chapter on different things. Chernobyl, the animals, the zone, the Michael Crichton speech, all that stuff. Okay, good enough. So you know what to study. Both of that's tomorrow for you. Your class had to split up. They had their essay part today. They'll have the actual test tomorrow, like you'll have the regular test tomorrow. Let's go over these. You ready? All right, first of all, this guy will be split up into 2 parts tomorrow. I need to go over it very quickly. We don't have a lot of time for the review, so you're going to have to help me out here. One of the things you will be given on the test is this number right here. That's c, the speed of light, 3 times 10 to the 8th, and most importantly, the mass of the proton, neutron, and electron. Okay? You're told it's PD 108. Now, I look up PD, that's palladium with 46 electrons, right? So he has 46, protons. 46 protons. He also has 46 electrons. How many neutrons would he have to have? Why 62? What'd you do to get that? Subtracted the 46 from 108. You'll multiply each of those by the masses, and I'm not going to waste my time doing that. The mass of the proton, the mass of the electron, the mass of the neutron. You would multiply each of those by that, and what will you get for this mass right here? How much?
108.901.
108.901. Does everybody agree? Yeah. All right. That is that's the mass that it should be. It's not that. What do we do to get the mass defect? Subtract those 2 and you get what?
You get 0.9971.
So 0.997 for significant figures. Everybody get that? Now, by the way, those units would be for an individual atom atomic mass units. But we're talking about a mole of atoms, so that would be that many grams. Now, that's not good enough. I want to get my answer in joules, and joules are kilogram meter squared per second squared, so I have to do what with that number? Did you remember to do this?
You multiply it by C.
No.
10.
Before I do that, I have to do what with this number before I do that? I have to convert grams to kilograms because I need my units in joules, which are kilograms. All right, per 1,000, I will get 0.000997 kilograms. Okay, that's the number I'll use in the next part. Which bit is right? We have to use E equals mc squared. This will be a second question on the test. A couple of mistakes here. Already we see one. By the way, this would be fine for the correct answer for the mass defect. But when you go to use it in determining how many joules of energy you're going to get, you have to convert it to 0.000997. All right, so 0.000997 kilograms times the speed of light, which is, I'm just going to tell you to use 3.00 times 10 to the 8th meters per second. But here's what people forget. They forget to square it. You got to square that number and then multiply it out. And then what do you get for your amount of energy in joules? Anyway? What'd you get? Nobody got it. Well, it was the first problem, so that tells me that either every single person did it wrong. 8.96 times 10 to the what? 13. Does that sound right, everybody? Okay. So all you had to do. This is not a hard problem, despite the fact that you are using Einstein's equation. It really isn't that hard of a problem. You just find the mass defect, subtract those two numbers, and then plug that into E equals mc squared. Okay? Got it? Good. All right. That's the first two problems on the test, guaranteed. Next questions are going to be half-life problems. In a half-life problem, you've got 1/2 to the x power, that's how many half-life you have, equals a over a sub 0. Now, the first thing you got to tell on this one is how many half-lives you underwent. It was 7 years you waited, the half-life was 4 years. It's not a nice, easy number. 7 years divided by 4 years is what? 1.75 years. So that's the number I got to put in for x. I told you have to do this on the calculator. That's why I told you better make sure you know how to do it on the calculator. 1/2 or 0.5 to the 1.75 power equals a over a sub 0. What was a sub 0? What was the initial amount you had? 30.0 grams. Everybody good with all that? Okay, now how do I plug this in? If you don't know, you should be doing it with me right now. All right, 0.5, raise it to the 1.75 power. What do I get for that answer? 0.297. Anybody else get that? Is that right? Okay. L equals A over 30.0 grams. Cross multiply. How much is left that's still radioactive? 8.91 grams. Got that for your half-life? I mean, I'm for your half-life problem. For the amount that's left over. That sound good to you? Okay. What's next? Well, another half-life problem. This one I purposely put on it because notice how it's worded. You can word these differently. Okay, let's write the equation down and get everything started the way we normally would. 1/2 to the x power equals a over a sub 0. But this time, we're not looking for how much is left. I'm looking for an age. The a over a sub 0 is basically, as I wrote in the problem, the fraction remaining. That's the fraction remaining, or the part remaining. And you might say to yourself, well, that's going to be 25%, right? 0.25, correct? No. 25% less activity is there. So there's how much activity? 0.75. So you actually have 1/2 to the x equals 0.75. That is confusing for people a lot of times. Okay? And it's because of the way it's worded. If I had said the activity now is 25% of what it was, that's different than saying it's 25% less now than what it was. Okay, that's pretty crazy, but you have to keep that in mind. You have to look at how things are worded. All right, how do I do this? Because I've got to solve for that x, and he is an exponent. Take the log of both sides. Log of both sides. Well, this is negative 3.01x, and this guy is negative what? For the log of 0.75? How much? Somebody? Everybody else get that? Right? So what does x equal? 0.415? Now that is how many half-lives it underwent. In other words, not even a half of a half-life. How long is one half-life? That long. So I multiply it by 5,730 years, and I get what?
2,380.
How much?
2,380.
2,380. Everybody get that for their number of years with how old that piece of wood is. Good. All right. Everybody go with that. Okay. That takes care of the first 4 problems on the test. However, the next section on the test is we have to go back now to this one here and do these. Okay? This is on the second half of the test, top side. And here's what you're going to have to do. Complete these equations with the correct particles or atoms. Tell me the type of radiation that was given off or captured, whatever, and tell me whether this is above or below the band of stability. You will know if he's above or below the band. Let me just real quickly before I start doing these. You'll know he's above or below the band because of the neutron-proton ratio. What happens to the guy? Seriously? Neutron-proton ratio, if it's too high, if I have too many neutrons, if you're above the band, I'm going to try to convert a neutron to a proton, or at least get rid of a neutron. Down here, I'm going to have too many protons, not enough neutrons. So you don't just have to memorize, where was that in my notes? Was it under Roman numeral 3A, B, C? No. You could just tell it by looking, or not looking at, you're not going to get this chart, you're just going to think. Did he convert a neutron to a proton? Then he must have been above the band. Did he convert a proton to a neutron? Then he must have been below the band. All right. And that's how what I'll be asking you, what would be more likely to have happened in that case. All right. Let's get back to my problem here. And let's do these. Now, these are actually, as I said, some college classes will begin with nuclear because in a lot of senses, it's easier than balancing chemical equations, especially when you get to the next chapter, redox reactions. They're going to have coefficients of 17, 25, 30, some in front of numbers, trying to balance out multiple compounds. This is really pretty easy. I got a 95 here on that side. I got a 95 here plus something. That must be a 0, right? It's got to add up. 240, 241, what must this be? A 1. Now you have a question at this point. You have to think, what is that particle that has an atomic number of 0, which means it's not a proton, yet it has a mass number of 1, which means that's mass number is protons plus neutrons. What must that guy be? A neutron. So this would be neutron emission. Right? Everybody agree? And if he's neutron emission, he's trying to get rid of neutrons. Probably where was he? Above. Okay, that's the kind that you would expect to get from somebody above the band. All right, let's look at this guy down here. I got a 1 here, but I've got a 2 there. I got to have a -1 there, don't I? 3 and 3 is a 0. What particle has a -1 for an atomic number and a 0 for the mass number? A beta particle, which is basically an electron ejected from the nucleus. So that's what this is, beta emission. Beta emission, right? If he's beta emission, let's look what he did here. How could you tell? It's not a matter of memorization. Oh, where was beta emission in my notes? No. It's a matter of looking at what happened to this guy. He had 1 proton, now he's got 2. And it didn't change the mass number. What happened to this guy? The neutron was converted to a proton, which I would expect from somebody above the band, right? All right. Let's look at the next guy down here. I've got 19 and I've got a -1. So that's easy. That's 18 over here, right? No, but that's what you will do. It's what many people do when they're doing these. 18 minus 1 is not 19. Okay? So what is the actual answer? 20. The 20 is the atomic number. Up above, that's a 0. This is still 42. So 42 and 20, I have to tell the name of that element. The guy who is element number 20 with the 20 protons, atomic number is calcium. Everybody got that? All right. Now that I know that's calcium and I know what happened to him, he gave off a beta particle, it's basically the same thing that happened here, only it was drawn a little differently. Here I wrote it as an electron, here I wrote it as a beta. I could do either one. It's the same thing. It's still beta emission, and it's still going to be above the band. Everybody agree? Okay. Let's look at this guy. I've got 94 on that side and a 2 over here. That better be a 90. I thought I had black here. I thought it should be a 92. Is that correct? The top number, a 4 here, but a 39, 239 there, so it'd be 230 what? 5. And what guy is 92? Uranium. Not my uranium, but uranium. And what happened in this case, he gave off an alpha particle. Now, it's not necessarily true that all things that give off alpha particles are necessarily above the band, but I said pretty much anybody over 82 is beyond the band of stability, and I would put above for him. And that is obviously alpha emission, because that's an alpha particle. Helium nucleus is an alpha particle, and I would put above also for him. One other thing about this guy I want to say, because I didn't put any in here like this, but I did on your sheet, and I will maybe on the test. Say there was a 3 in front of this guy. A lot of people, when I passed that back the other day, maybe have noticed towards the bottom, they have almost everybody had one wrong. About at least 3/4 of you had it wrong. If I had 3 alpha particles given off, what would I have to have done? Multiplied these, you know. And a lot of people didn't see that. There was one that was actually had a 4 in front of it. All right, last one down here, 19. This guy's got 18, so he's got to be a +1, correct? And this guy up here is still a 0, 37, 37. What has a +1 and a 0? That thing's called a positron. And when that's given off, what do we know is happening when a positron is given off? What must have happened? Well, just look at what happened. He had 19 protons, now he's got 18 protons. What happened? He converted a proton into a neutron because the mass number didn't change. So he would be below the band, correct? All right? All right, sounds good. I don't think there's anything else to tell you. I would study those packets for the reactors. I would also look over the health stuff and in my notes. The equations you should be good on, and so should you be good on the half-life and the other.